Today, we are cracking the code on one of the biggest, toughest challenges in AI. How do you actually train an AI to reason? For years, it's been this chaotic, super high-stakes gamble. But what if you could turn it from an art into a predictable science? Well, a huge new breakthrough suggests you can by giving us something we've been missing all along, a blueprint.
I mean, that's really the question, isn't it? This is what AI labs have been wrestling with for ages. Teaching an AI to think has been less like engineering and a lot more like, well, alchemy. You're just mixing all these expensive ingredients together and hoping you stumble upon gold. It's an incredibly costly guessing game. But now, it looks like someone's finally drawn a map.
So let's break this down. An AI model gets its raw knowledge from something called pre-training. But to really unlock those advanced skills, like step-by-step reasoning, you need something called reinforcement learning, or RL. You can think of it as teaching an AI by rewarding it for good decisions, kind of like training a dog. The problem is, this whole process has been the absolute Wild West of AI development, totally unpredictable, chaotic, and just unbelievably expensive. Yeah, up until now, there really hasn't been a proper scientific method for it. All the progress we've made has come from trial and error on a massive scale. And that means progress has been slow and it has been very expensive. You literally couldn't know if a new training technique was going to work until you'd already sunk millions of dollars in compute time to try it. So to find a better way, a team of researchers went on this massive undertaking. They ran a study that used over 400,000 GPU hours. To put that in perspective, that's like running a high-end gaming PC nonstop for almost 46 years. It's a colossal investment, all aimed at one thing: finding a scientific framework to finally tame the chaos of RL. The main mission here was to create a real science of RL scaling. A great way to think about it is like a growth chart for a kid, right? Where you can predict their future height based on their early measurements. That's exactly what they wanted to build for AI, a tool that could look at its early training and predict how powerful it would ultimately become. And that brings us to the core idea here: predictive scaling. What the researchers figured out is that an AI's learning progress doesn't just go in a straight line. It follows this very specific S-shaped curve. And by fitting the early data points to this curve, they could basically see into the future and forecast how smart the AI would eventually get. The key is understanding the three parameters that define this curve, starting with the big one, the ceiling. First up, you've got parameter A, which is the ceiling. And this is maybe the most important of all. It represents the absolute maximum performance an AI can possibly reach with a given training setup. It's the performance limit, the hard cap. So the recipe you choose as a developer literally sets a limit on how smart your AI can ever become. Next, there's parameter B, and that's all about speed. This one determines how steep that learning curve is. So a higher B value means the AI is way more compute efficient, it learns faster, and it rockets towards its performance ceiling using way less training time. It's all about how fast you can climb the mountain. And finally, we have C-mid, the midpoint. This is a super practical one. It tells you exactly how much compute, how many of those GPU hours it'll take for the model to get halfway to its full potential. It's a key milestone that tells you just how much investment you need to see some really serious progress. Okay, so here's where it gets really fun. When the researchers applied this new framework across their massive 400,000 GPU hour experiment, they learned some incredible things. In fact, they ended up busting 3 pretty common myths about how you're supposed to train AI. Lesson 1 is huge. Not all peaks are equal. It turns out that the training recipe you use doesn't just change how fast an AI learns, it fundamentally changes its maximum potential. Simple choices like how you measure the AI's mistakes or how much data you show it at once can dramatically raise or lower that ultimate performance ceiling we just talked about, that parameter A. This brings us to lesson 2, and I absolutely love this one: the hare versus the tortoise. So take a look at this. In the early stages of training, a very popular competitor's recipe, that's the hare, is clearly winning. It's learning super fast, looks like a rock star. Their own new recipe, called ScaleRL, is the tortoise. It's starting out a bit slower. But then, when you let the training run longer, the whole story flips. The hare hits its performance ceiling and just flatlines. It can't get any smarter. Meanwhile, the tortoise, ScaleRL, it just keeps on climbing, and in the end, it reaches a much, much higher level of performance. It's this perfect illustration that early speed can be really deceiving. What really matters is having that higher ceiling. And that leads to the third and final lesson. Efficiency isn't the same thing as power. The data show that a lot of the popular tricks and tweaks that researchers use, well, they don't actually make the models smarter. They just make it learn faster. So in our language, they improve parameter B, the speed, but they do absolutely nothing to raise parameter A, the all-important ceiling. So, with all these lessons in hand, the researchers developed what they call ScaleRL. And here's the thing. It isn't some brand new magical algorithm. Instead, you should think of it as a meticulously crafted recipe, one that combines all the best-known ingredients in just the right way, a way that is now scientifically proven to scale predictably. And here's just a little taste of those ingredients. Now, don't worry, you are not going to be quizzed on what truncated importance sampling loss means. The important thing to know is that every single component here was chosen not by guesswork, but through massive, rigorous testing to find the combination that gives the highest possible performance ceiling. It's a real shift from inspired art to principled engineering. All right, now for the grand finale, the ultimate test. Because, it's one thing to have a theory and a recipe that works in smaller tests. It's a whole other thing to bet the farm on it. So that's what they did. The researchers decided to put their entire framework on the line with one single, massive 100,000 GPU-hour training run. And here's how they set it up, which is brilliant. They started training an 8 billion parameter model. But right at the halfway point, after 50,000 GPU hours, they hit pause. They took all the performance data they had so far, they fit it to their S-curve, and they made a prediction. A precise mathematical prediction of exactly where the model's performance would be after the full 100,000 hours. This really lays out the whole experiment. For the first 50,000 hours, the status is measured. They're just collecting data fitting their curve. But then, look at that second half. The status is predicted. They literally drew a line on the graph into the future, making a specific forecast about what was going to happen in territory they hadn't even explored yet. So this was it, the moment of truth. Was their scientific approach actually going to hold up? Had they really managed to tame the wild, unpredictable beast of reinforcement learning? Or was reality about to take a sharp turn, wasting tens of thousands of hours of incredibly expensive computer time? They pressed go on the second half of the run, and the result? A perfect match. The actual performance data from the next 50,000 hours landed almost exactly on the curve they had predicted. It actually worked. They had successfully forecasted the outcome of a massive AI training run. They'd proven their framework was robust, reliable, and most importantly, predictive. At the end of the day, what this research really represents is a fundamental shift in how we can build advanced AI. It's moving the entire field away from that world of unpredictable guesswork and high-cost gambles, and moving it towards a true scientific framework that allows for predictable scaling and much, much faster development. And this leaves us with a pretty wild final thought to chew on. This breakthrough gives us the engineering principles we need to reliably, predictably scale up an AI's ability to reason. It gives us the blueprint. So the question is no longer if we can build AI that surpasses human reasoning. The question now is, what do we want to build now that we finally know how?